So how does it work? And can you use it? So we know that solar particles are doing something, but how can it work? If you understand how it works, you might be able to use it, which we can to an extent. Now, we've established that the effects from the sun come in bursts. We call these red spikes, or when there's a group of red spikes, we call them SWIPs, solar weather impact periods. Now, I won't go into how we predict these, but they're about something coming from the sun, something about motion in the solar wind and its linkages with the Earth. Okay? We can predict when these will occur. Just to give an example, we didn't know this at the time, but we had a very particular interesting SWIP or red spike, which in my calculation was going to be very important. Then I read, or I think Ulrich told me, where's Ulrich? Do you want to wave Ulrich? There he is. He told me, he said, Piers, there's a sudden stratospheric warming on. A sudden stratospheric warming happening at a certain type of SWIP. Now, the sudden stratospheric warmings are very, very important, especially this one, which is the biggest one for 30 years, and it triggered that crazy activity in the jet stream, which resulted in that catastrophic snow in the United Kingdom. Okay, so we're getting into a situation where will be able to predict these. Now, this has turned you all off, I know. Anybody remember differential equations?
Yes.
Hey! Right. Now, okay, we're going to simplify things. Basically, standard meteorology solves a whole lot of differential equations for the Earth. They say, oh yeah, closed system, blah blah, this equals that, that equals that, this is, depends on this, and so on. So, imagine this as the Earth's atmosphere, right? So it's a differential equation, and you hit it, something happens. And standard meteorology, you predict what will happen. Okay? They can look at the atmosphere now and they say, well, we know it works, therefore it's going to go there. Okay? It does. Well, it does, a day ahead, or 2 days ahead, or 3 days ahead, but 4 days ahead, doesn't work. What has happened? Well, there's an external influence. You see, they know what's going to happen then, but they don't know that actually this is going to happen, 2 days' time. We know that this is going to happen in 2 days' time. So, they solve what's called the transients. Okay? They solve this. Lots of equations for the world equals nothing. The answer is a standard meteorology forecast. We solve another equation. Lots of equations for the world equals weather action indicators. The weather action indicators describe these SWIPs, when they're going to come, and other modulations, such as what is the moon doing? What is the moon doing? Now you add up these two things, FSM plus FSW, they are a solution as well. But the FSM just is a transient, it disappears. So it's of no value for forecasting. But why can we actually get anywhere with this? Let's just say we know these equations are too complicated even to think about, let alone write down. So how the hell can we find answers? Well, we do. Okay. Let's go to the next one. So there's a concept. Here's the world. You could draw a pressure map around there. You could have a pressure map here, pressure map all over the world. You can describe the weather state of the world as a total weather state on pressure maps. So the SWT is going to somehow predict what we call the total weather state, the TWS. An SWT state is about the forcing factors which cause the weather. So what I'm saying is that we know that over periods more than 4 days ahead, there's external factors are dominant. If we can predict when sometime in the future is going to have the same sun, earth, weather, magnetic forcing factors described by an SWT state, we say that's going to happen then, or then rather for you. And the last time that happened was then, we'll say, well, okay, the weather then, which is driven by those factors, is going to actually be similar to what the weather will be, is driven by similar factors. Of course, they're not easy to find. And it's not the same as saying, oh, if it was raining then, and we had a period of similar weather then as we just had, then we're going to have more sort of similar weather? No. Because these SWT states don't appear in the same order in the past as they do in the future. So you're going to have, like, weather goes, in the past goes A, B, C, D, E. In the future it might go E, Z, Q, W, A, B, whatever. So you're going to have a join-up problem. But nevertheless, if you know where to look in the past, you can make a forecast, which is what we do. Those of you that recall ideas of phase space, you know the phase space? Sort of, one person's pointing at his head. No, that's he's not there. Okay. Right, it's just to say that weather repeats. It comes back. There's nothing new going on. Nothing new. Similar states are coming, i.e. states in phase space are nearly repeating at predictable times. But why can we actually do it? Well, the reason why we can do it is because the external forcing factors described by the solar weather technique are more important than internal weather noise transients on reasonable timescales of only 4 days. But now you think about this question. There will always, for any differential equation, there will be a transient solution. And it always dies out in time. So there will always be a time ahead whereby an external forcing factor, however small, will take over. But the issue is how long do you have to wait? And actually it appears for the Earth as now, it's only 4 days. If it was 100 years, we'd be wasting our time. But the external factors are big. The Sun, Earth magnetic loops are big. The poleward changes in energy flow are big. And that's why it actually works. This is just a point I made, but beware. You can't just look at the weather in the past and say there's one forcing factor that causes that. See, when it rains, there's many reasons why it rains. It might be SWT, column vector, 1 to 100, or whatever. You know what I mean? There's many different causes for it to rain. And you see, we don't solve any equations at all. We just know, well, maybe some equations exist, and we can understand where there's similar forcing factors. So it's a bit like quantum mechanics. Now, I say this because I remember Harry Fairbrother, I don't know if he's still, but he was a top flight, he was a technician in Imperial College when I was a student, really tremendous fellow. And he came to one of my events a while ago and he said, Piers, I think we do it by something like quantum mechanics. And I thought, Jesus, I do, but I hadn't thought of it like that. And that has helped me, just that single statement from him. He was a maths lecturer, actually, not a technician, he was chairman of the ASTS. We generate rules which enable us to look back. So the future states are going to be A, B, C, D. We can work out the future SWT states and look in the past to past similar SWT states called different states. And there might be more than one of them. And if you find, we think, oh, there's something which might cause, well, we've got a solar weather state here. We look back there and we find there's one here and there, and if they both say snow, we say snow. Grey day. If one says snow and the other says warm, we say come up and give it a C, a confidence C. But you have to use judgment. But this enables us to give relative confidence between forecasts, and the relative confidences do work. If we say A, we are definitely more likely than if we say C, we're not. Now, it's an example set. This is just to say, using these sweeps and look-backs, weather action scores 85% of extreme events. 85%. Big extreme events. Maybe the chance of each of them happening by luck would be, I don't know, 1 in 5, even if it's 1 in 2. It's, you know, we win on William Hill. Well, I've been down from rugby gambling with William Hill for reasons explained here.